Okay, well, welcome to the Geology of Joe's. I'm Paul Anderson, and I'll be your instructor. I'm a mostly retired consulting geologist. I've worked in the state of Utah most of my career, and a good portion of that has been here in central Utah in the Cretaceous rocks that surround Joe's Valley and that you so enjoy bouldering in. I wanted to give you some introductory information about the rocks that you're going to see. I'm going to start with a little bit of geography, a little bit of geologic history to sort of set the stage for these favorite rocks that you love to climb in. So to start with, I'll start with this graphic of north central Utah. This is a satellite image, and you can see sort of a potato-shaped brown color in this portion of the illustration or the image, satellite image. This is the San Rafael Swell. And the San Rafael Swell plays a fairly important part in the history of, or the modern scenery that we see today in this area. It's a swell in the sense that this was an anticline. This was a bulge up in the earth, but instead of being a domal shaped, it's elongated, and so geologists call that an anticline. And around the outside edge of the anticline, the beds slope or dip, as geologists call it, away from its center. And on this side, Castlegate happens to be about here on the west flank of the San Rafael Swell. These dips are fairly gradual, about 5 or 6 degrees. On the east side, if you've gone across I-70, you'll know that the east side of the San Rafael Swell, there's a very steep dipping. It's called a reef, the San Rafael Reef, and the beds are dipping about 70 degrees. So this is what we call asymmetric because it's not dipping the same on both sides, an asymmetrical double plunging anticline. Now there's a mouthful for you. And around this, you see this dark green band. This is the Wasatch Plateau, the high country of the Wasatch Plateau. Circling around, Price is about up in here. The Book Cliffs come down around here and continue off into Colorado. So that's sort of our geographic setting. At a more detailed scale, this is a Google Earth image. Here is Castledale in Orangeville, and this is Straight Canyon and Cottonwood Canyon, where most of the popular climbing spots are. And you'll notice that the darker colors up here reflect more concentrated, deeper green vegetation of the Wasatch Plateau and the ag fields out here in green around Orangeville and Castledale. In this brighter, lighter colored zone here, we have some very bright light spots, and that's the exposure of the Manco Shale. And the Manco Shale sits at the base of the Wasatch Plateau. And we'll drive through that as we go up towards the canyon this morning. And in here are some little white spots, and they are places where a gas exploration company has cleared the vegetation, and these pumper jacks that you see, if you've traveled up and down this road, you've probably seen them. And they're not pumping oil, they're actually pumping water, and they're trying to get the water extracted from an underlying sandstone similar to what we'll be crawling through, which contains coal. And this underlying sandstone, called the Farron sandstone, has coal beds, and they've drilled down into that, pumped water off, and once the water is off, then the coal has gas absorbed onto the coal molecules. They will then release that gas, and it can then flow into the well bore, and they collect it in a system, and I think there's a collection point and a compressing station that you pass on the way up and down the canyon. Anyway, that's what all those little white dots are on these pediments. And pediments are just debris that has tumbled off and been washed with some sheet flow action off the face of the cliffs as these steep cliffs are eroded and retreat through time. One other feature here that I want to point out is Joe's Valley Graben. So you see this very linear feature in the graphic, and Joe's Valley Reservoir sits in there. And of course it wouldn't be there unless man had plugged up the hole and created a big dam that makes a nice reservoir site here. But this sits right on a fault. There's one fault here and another fault back here that run north, almost north-south, and the center part of this valley has been downdropped. So geologists call that a graben, where there's a fault on each side with a downdrop block in the center. And the offset on this is over 2,000 vertical feet. So these are very large faults with a very large downdrop block in the center. Okay, a little cross-section across the west here in central Utah. This was drawn by a fellow named Armstrong back in 1968. It's still a really nice illustration. We call it a stratigraphic cross-section, showing the stratigraphy of this particular Cretaceous age. So you kind of have to erase your mind from that prior image of the Rafael Swell, and we're going to go back in time about 100 million years, and this was the sort of the depositional pattern that we saw. You can see that on the western side of this cross-section, we have thrusted mountains. These are thrusted crust sheets. Thrusted crust sheets, that's correct. The Pacific plate was crashing into the North American plate and compressing and subducting, and in that process it pushed some thin-skinned slabs of crust, several thousand feet thick, eastward, and these piled up into what's called the severe orogenic high. And this orogenic high, this mountain range, went from Mexico all the way to Alaska, north and south, up the western side of North America. Well, as soon as you stick your head up, right, somebody knocks it off. And indeed, once these mountains were formed, erosion started to work on them, and rivers flowed out to the east. And when you pile something on top of a crust that's not rigid, I know that when you fall off a boulder, you feel like the crust is rigid, but actually there's a small amount of absorption that goes on, and we call this this deformation, this tectonic deformation that takes place. So if you load the crust up with a lot of weight, it's going to push it down and create a sag out in front of this big loaded mountain zone. So we call this a 4 deep, and this is a perfect place to put all of those sediments that are being eroded off of the severe orogenic high. The reds are conglomerates, the yellows are sands, and the browns are shales. Now we'll see the brown Manco Shale. It's just right outside of town here. And we'll look at all of these sandstones when we get up in Straight Canyon. And they're stacked up in formations. I know you can't see it from this graphic, but we'll go over it in the next graphic. But Star Point Sandstone, Blackhawk, and Castlegate Sandstone. And you can see that the Star Point is interfingering with these Manco Shale, this brown Manco Shale here. And we'll see a nice example of that as we drive up into the canyon. So just a little, believe it or not, kind of information about sagging crust. For those of you who are from the Wasatch Front, Antelope Island sits in the middle of the ancient Lake Bonneville about 12,000 years ago, or about 17,000 years ago. It was as high as, it reached its highest level, and then it drained out into the Columbia. And at that time it formed what's called the Bonneville Bench. And the Bonneville Bench elevation on Antelope Island is 150 feet higher than it is, say, down at Nephi. Well, why is it higher? Because water seeks a nice flat surface. The reason is that as Bonneville evaporated, Antelope Island has come up because of the buoyancy factor of the Earth's crust. So it's actually moved 150 feet up from its prior level during the peak fill of Lake Bonneville. And so that's the phenomenon that we see here, this sag in the crust, this isostatic adjustment based on weight. This is the illustration of the local stratigraphy, Star Point Sandstone, Blackhawk Formation, and Castlegate. And I'll bring this out a couple of more times as we proceed through the field trip. The grays are shale, very fine-grained material. The bright yellows are sand. And in this case, in all of these rocks, probably the coarsest sand that we see is maybe about, well, it's called coarse grain or gritty. So it's not, there's no boulders or conglomerates in here. These are all really purely sandstones. Here you see a couple of black lines. This represents some of the coal seams that are very important to this area and have been historically exploited over the last 50 to 100 years. And above those is a little pink that to illustrate when these coals naturally burn, they oxidize the overlying rocks. And we'll talk a little bit more about that at our next stop. But you'll notice this pattern that there's a steep cliff with the star point, then kind of a steppy erosional pattern, then a steep cliff with the Castlegate Sandstone. And the best boulders are here in the Blackhawk Formation. A little bit of a back to paleogeography. I mentioned this, the severe orogenic high, and this is an illustration from Blakey, who does beautiful paleogeographic maps. And he shows the severe orogenic high here along the edge of the North American plate. This is the Pacific plate that's colliding with it during this particular mid-Cretaceous period. And it forms this sag out in front of this loading, and this is called the mid-Cretaceous Seaway, or a four deep, and you could sail from the Gulf of Mexico to the Arctic Ocean back then. It was kind of a semi-tropical climate. We had 2,100 parts per million CO2 in the atmosphere. Today we have, what, over 400. So much higher concentration of CO2, a much warmer planet back then. Here are a couple of illustrations of, again, of Blakey's paleogeographic. This is 87 million years ago, and this is 65 million years ago. And this is the Cretaceous Seaway that I mentioned, and here's the state of Utah outlined with a little bit of a dark outline. And you can see that the shoreline has gradually prograded, as we say, from west to east, filling this big foreland basin. So this would be kind of star point sandstone time. We're about here in central Utah. And this would be Blackhawk time, we're about here. So you can see in Blackhawk time, we had a lower coastal plain, lots of streams flowing across it towards the shoreline, which was further to the east at that time. And you'll see the difference in the rocks as we proceed today. So this is just a quick picture of where we're headed. And we'll see those three formations, the Star Point Sandstone, the Blackhawk, and the Castlegate, at our first stop as we proceed up the canyon. Okay, well, we're here at the intersection of State Highway 29 and a road that takes off to the right as you're going up canyon, up Cottonwood Canyon. There's one other paved road that you pass coming up from Orangeville to this point, but we turned right off of the main road up Straight Canyon, and we're here near a cattle corral for a stop if you wanted to repeat this venture yourself. So the purpose of this is to try to introduce to you the stratigraphy that I talked about in the introduction down at the rock shop, just to give you some basics, try to tie some of that material into what you see here in the cliffs. So just a reminder, I showed you this before, I'll just review this graphic, but we're going to look at three main formations here, the Star Point Sandstone, the Blackhawk Formation, and the Castlegate Sandstone. And the Star Point Sandstone is the lowest cliff former, you can see here, and the Castlegate Sandstone is the very top of the cliff, and it's a very vertical face. In this graphic, just to remind you, the bright yellows are sandstones and the grays are shale, and the blend of color in between is this gradual change from dominantly sandstone to dominantly shale. You'll also notice that we have a couple of coal seams in here. These black lines are coal seams, and we have those up here on the cliff face behind us, and I'll point those out in a moment. Also, you'll notice I've put a little pink color in there, and we'll see that pinkish red color on the outcrop as well. So this is sort of an overview of again, the stratigraphy from a different view. It's taken from down the canyon at the point back behind me here at the intersection of these two. And the lowest formation is not on the graphic I showed before, but it's called the Manco Shale. And as we look around here from this vantage point, we can see in the low hills below the cliffs these gray slopes, and that would represent the Manco Shale, which is these offshore, shallow, marine depositional environment for this particular gray shale. I also mentioned at the beginning of our introduction that these Manco Shale slopes are covered by pediments. And a pediment is a poorly sorted, big boulders, giant boulders to sand and mud, and they drape down off of these cliffs, and you can see that back behind me. And if you look down canyon, you can also see that as well. So these pediments are here as a result of the Wasatch Plateau cliff face retreating back to the west and leaving their mechanical erosion remnant strewn down onto these aprons. We're going to move up canyon in a minute, and we'll see another view of this. And this is also behind me here, but I put those little pink layers on that cross section, and you can see those back in the cliff face here, and they lie above the Star Point Sandstone in the Black Hawk Formation, and they're usually concentrated in the lower portion of the Black Hawk because this is where the thickest coals lie. They usually lie right above the Star Point. Now remember, in our little introduction, the Star Point Sandstone is our beach sands. So these are our beach sands. The Black Hawk represents that lower coastal plain, overbank deposits and flood basin deposits where we see a lot of these peat swamps, and where these these peat swamps seem to be best developed right above the beach. As the beach progrades into the basin to fill it, these peat swamps develop right on top of those. And we know they're there. It's hard to see any coal from this vantage point, but we can see this red color, and the red represents iron, or oxidation of iron minerals to red when the coal seam burns. Now, a coal seam can start on fire in several ways. Within the coal seam, there are impurities, and one of the common impurities, a mineral impurity in coal, is pyrite. And iron pyrite will oxidize when water and air gets to it. So as the cliff retreats, the erosion and the deterioration of the front of the cliff and the fractures in the rock allow water and air to get into the first, anywhere maybe as far back as 1,000 feet. So this process then oxidizes the pyrite and can spontaneously ignite the coal. So that's one way it can start on fire. A second way is by lightning strike, and a third way, which is kind of related to the second, is by a forest fire. Some people say that Native Americans may have actually lit some of these coal fires in the past. Who knows whether that's true or not. But anyway, the red color tells you that there's a coal seam nearby, and during the burning and the oxidation, it's colored the rocks above it and near it this red color. So we call that kind of a coal bloom. Okay, so now we're panning from the top of the cliff, and this is at that point again at the Cottonwood Road, the Cottonwood Canyon Road and the Straight Canyon Road. And we start with the Castlegate Sandstone at the top. It's kind of a tan, bland looking sandstone, but a nice vertical face. And then we come down the canyon, lots of tree covered slopes and little cliffs that are, say, anywhere from 10 to 40 feet high. There are not too many of them here in this exposure, but quickly we come into the red, the coal bloom that I talked about zone. And then below that kind of steep slope of the coal bloom, we see a lighter colored sandstone that's running across the canyon. And this is the top of the Star Point sandstone. And the Star Point consists of several benches, if you will, or cliffs. And as we come down from the top one, you'll see that some of the red from the bloom or the burning of the coal has washed over the top of some of these Star Point sandstone ledges, coloring them a little bit pink. So if you see a vertical down, going up and down the cliffs, you can follow that pink color, then it's more likely draped down with water running over the cliffs, and it's not really coal bloom. So other than watching out for that, when you see it in the broad horizontal following the strata, that red is related to burning coal. That's a pretty good introduction here, so we'll move on to our next stop. Well, this is our second stop out in the field, and this is a mile or so up from the intersection of Cottonwood and Straight Canyon. We're on the west side of the road here. And the reason to stop here is just to talk a little bit more about the Star Point sandstone, which, as you will recall, is a shore face sand or a beach sand. We geologists call it shore face because we include not just the top of the beach where it washes around your ankles, but all the way out to where we lose the sand into a depth of, say, maybe 10 meters. So behind us here is just a quick review of the stratigraphy again. We have the Star Point sandstone and the Black Hawk Formation, which is getting hard to see because it's so steep, but you can kind of see some stair-stepping fluvial or stream deposited sands with the Castlegate on top. And also in our view here is a beautiful exposure of the coal seam. It's probably around 10 or 12 feet, and it's not burned right here. It's intact, exposed in the cliff face just above the top of the Star Point sandstone. Now, the Star Point sandstone, or shore face sandstones, how do we know that we're looking at a shore face sandstone versus a fluvial sandstone? We have a couple of boulders here behind me, and I can identify those positively as part of the Star Point sandstone. And the reason that I can do that is because I'm walking on the shoulders of many others who've come before me. A lot of this work was done on Galveston Island. Houston has been an oil center for many years, and a lot of geologists would go to Galveston Island on the weekends, and they, I'm sure, got to thinking, wow, this would make a great oil or gas reservoir. We ought to know and understand a little bit more about the nature of this thing. So sedimentologists were kind of attacked this problem, and academics as well were funded by oil industry, and they did a lot of studies of modern beaches. And from those studies of modern beaches and how the sediments are organized, the grain size, the size of the grain of sand, does it get smaller, does it get bigger with depth? If you were to do a little vibrocore down through here and look at the sand, they came up with these models of beach sands, published on that, and then geologists after that, like me, read those papers and become familiar with what's called the sedimentology, or how the sediments are organized and stacked in these different environments of deposition. So I can look at this rock and identify whether it's from a stream or from a shore face, and this is certainly shore face rock. Now, why is this relevant? Well, when I came on the tour, or came up the canyon with Adriana and Steve, they were showing me the rocks that they like to climb on, and they didn't like to climb on these rocks. So that was kind of interesting, that here's all this Star Point sandstone, and there's some big boulders, but they called it choss, not desirable, I guess, for climbing on. But on these boulders, you can see some of these little signatures, if you will, identifying them as shore face. They have parallel laminations. They have a lot of little burrows in them, little round burrows that are identifiable as a burrow that occurs in marine and brackish water type of sediments. So by looking at these, we can identify that they come from the Star Point sandstone and not from the overlying Black Hawk. This illustration, by the way, was put together by a colleague of mine, Tom Ryer, who is since deceased. But we used to call these Ryer's bananas because these shorelines prograde out into the basin with time, and they kind of look like a little yellow banana. Yellow is often used by sedimentologists as a symbol for sand. Okay, this is stop number 3. We are in the main part of Straight Canyon with the stream behind us. I think this is called a Minecart Boulder, and there's a wide parking spot here with a day use parking only sign to help you find the place if you're looking for it. This is a photo of the hillside just directly behind us across the creek. And I just wanted to point out our formations here. We have the Star Point Sandstone low just above the creek. And you'll notice that we don't have a big sharp cliff face like we do normally when it's on the other side of the canyon. We have a north-facing slope here on this side of the canyon, so the some of the erosional characteristics of the formations change a little bit. I have a dashed line through here for the top of the Star Point. It's a little difficult to pick out. But then above that, of course, would be our Black Hawk Formation. And this first big sandstone that we can see back here, this cliff-forming sandstone in the Black Hawk, is a stream channel deposit. Geologists call these fluvial rocks. I'll try to stick with stream. If I slip, you'll know what I'm talking about if I say fluvial. But one of the things that you can do from this vantage point is you can follow that particular stream-laid sandstone and see it across the canyon, and then you can follow it up the canyon from the other side, and you'll notice that it pinches out. It disappears up canyon. This is very characteristic of fluvial rocks. They tend to be laterally less continuous than the shore face rocks of the Star Point Sandstone below. This is also a really nice place when we look up canyon from this vantage point, where we can see this step outcrop of the Black Hawk, a vertical face 10 to 40 feet, then a little step back, another one, and a step back, and another one. And those 10 to 40 foot exposures of stream deposited sandstones, when they break off and roll down the canyon, those are the boulders that you really love to climb on. And that one of those is right behind me here at this Minecart Boulder. So what I'd like to do is I'll point out some of the features that we see in this boulder. We see, for example, a lot of soft sediment deformation. In other words, swirly bedding on rocks. Sometimes we'll see little holes in the rock when they weather away, and in those holes are actually logs and sticks and debris that has washed down into the stream deposit. And when they're eroded away, they're actually coal. Sometimes you can actually find them as coalified logs. But coal erodes away easily, so they make good little finger holes and grip holes for you to climb on. We'll also see something in this boulder called cross-bedding, where we see the laminations in the sand sweep across in a sort of an arcuate stacked formation, I guess you'd call it, or lamination. And these are characteristic of fluvial rocks. Oftentimes at the base of these channels, you'll see big holes and very chaotic bedding, and that is the bottom of the channel oftentimes is the highest energy, and so it will bring down other rocks and logs and debris. And sometimes they'll roll clay, if there's a clay in the bottom of the channel, and these are called rip-up clasts, where they're ripped up when the channel moves and changes and avulses. So these are all characteristics of channel sandstones that we see and can identify. One little note that you should watch for when you're climbing is the base of these channels will oftentimes have dinosaur footprints on them. So I don't know of any specifically in the canyon, but I'm sure they're here. And as you climb around, if you can identify where the bottom of the channel or the boulder is, whether it's upside down or right side up, which you can do by those bedding structures, you may actually encounter a dinosaur footprint impression. Okay, so this is a band in through here of woody debris, material that has been incorporated in the flowing stream, probably a little less current here, and gets caught up into the sand. And when it erodes out, you get these little holes, which I'm sure are good little hand and foot holds at times. Now, some of these can be actually clay galls or a clay ball, and some of them are wood debris that have eroded out. And unless you can actually see what's in there, sometimes it's difficult to say. But very typical of stream deposited rocks and very atypical of a shoreline or a shore face type deposit. Okay, this is a nice face here. This odd feature here is a concretion of some type. It means that it wasn't originally there when the sandstone was deposited. We call it a post-depositional diagenetic feature, and these are oftentimes very, very well cemented. In here as well, we can see some beautiful examples of these crossbeds, and these crossbeds can tell you which way is up and which way is down on a bed. We call these trough crossbeds, and they kind of have a trough shape, and you can see them coming down like this into kind of what we would call a bed set bottom. And these things, the convex part is pointing up, and that is the top of the sand. So when you look at these things, you can identify where the bottom of the sand was. This is, of course, fallen off the cliff face, but we can tell that that's the bottom of the bed, and this is the top of this stream-laid deposit based on the curvature of these crossbeds, and you can use that too as well. So the bottom of the bed's where you'd be looking for your dinosaur footprints, not the top. Very typical of stream-laid deposits. Okay, so this is one of the other sedimentary features about stream-laid deposits is called soft sediment deformation, and you can see the lamina coming down here, and they're fairly organized, and then they kind of twirl around and they get all contorted in through here. And it's a common phenomenon in sands that are rapidly deposited. There's some fluid escape that takes place and creates sort of this contortion or this swirling effect, and so you commonly see those in fluvial rocks as well, and they're very uncommon to see in shore face beach rocks. They do occur, but they're not very common, whereas they are fairly common in the stream-laid deposits. Okay, now we've walked around the boulder. I wanted a couple more graphics, and we'll wrap this up. This is a picture of a modern stream on the north slope of Alaska. And this is kind of a model for some of these fluvial rocks that we see here in the Blackhawk. You'll notice the dark blue is the active channel, and that you'll see these little abandoned meanders all through here. And we call this a channel belt, where this channel will move back and forth within this belt. And when it does move back and forth like that, it deposits a pretty thick continuous sand in here with a lot of discontinuities that some of which I'll point out in the boulder. But we call this the channel belt, and this the active channel. And these in the Blackhawk tend to be from a couple of 100 yards to maybe maximum a half mile wide. So that's when we looked at this, some of these channels here in the canyon. When you follow them with your eye laterally, you don't see them go too far, because eventually you come to a floodplain deposit or a pinch out of this channel belt. Now to the final answer about why are the fluvial rocks better than the beach rocks in terms of climbing? So the beach deposited rocks tend to be choss, so I'm told. And the river deposited rocks, like the boulder behind me, these tend to be the rocks that are desirable for climbing. These numbers here, 5.5% cement and 17.8% cement, I think answer a lot of the question as to why one is better than the other. So the beach deposited rocks only have, when we divide them up into grains, void spaces, and cement, they only have 5.5% of that rock volume is actually cement, whereas in the river deposited rocks, 17.8% is cement. So more than 3 times as much cement in the fluvial deposit, or in the stream deposited rocks, than in the shore face rocks of the Star Point. So this would be Star Point, and this is Black Hawk. And here we have what's called a photomicrograph of a rock with a lot of porosity and very little cement. It doesn't happen to be Star Point sandstone. And this is a picture of a sandstone with very little porosity and almost 100% cement. Now the cement is kind of this gray color, and the bright colored grains are different minerals. So these have been slabbed to 2 millimeters thick and then light projected through them, and geologists can use these to identify the type of sand in the sandstone, the type of mineralogy of the sand grains, and they can also evaluate how much pore space there is. Here the pore space has been dyed with a blue color. That's why we get all these little blue spaces. That's actually void space, not a mineral. But here those void spaces have been completely filled in with cement. So you can imagine that that makes this rock a lot looser and more, we call it friable as a geologist, but I guess you call it choss, whereas this is very solidly cemented and makes a lot of good handholds and footholds for your climbing. I think a couple of other things about this location that makes it so popular: one, it has a paved road running through it, it has a beautiful stream in it, and the canyon is fairly narrow. So the rocks are there's a high concentration of boulders in the area. But with those other factors added in, I think the real story here in terms of why are these Black Hawk boulders so much better to climb on than the Star Point and the Castlegate is that they're so much better cemented. So thanks for your attention.